Modern GPUs deliver unprecedented performance. With high memory bandwidths and several thousand processing cores, they provide all the power necessary for processing the standard stages of a graphics pipeline in parallel. Although the original fixed function pipeline has evolved to become more versatile, there are still many restrictions on what can be processed in it. There are many applications and techniques that could benefit from efficient parallel execution as part of the graphics pipeline. We present a high-performance software graphics pipeline architecture based on a sort-middle approach, splitting geometry processing and rasterization into separate stages. A persistent megakernel takes control of the GPU and ensures load balancing and effective scheduling. We provide a prototype implementation of our approach named CURE. The name CURE stands for CUDA Rendering Engine. It implements a complete streaming pipeline from vertex to frame buffer and is fully programmable. We have evaluated CURE extensively to identify its strengths. The main benefits of CURE compared to other software pipelines are its low memory footprint, its ability to handle versatile rendering scenarios, and the ease of adding extensions. Previous approaches to software rendering on the GPU usually involve straightforward passing on of data through the stages of the pipeline. This can result in high memory demands. In contrast, the scheduling in CURE makes sure that data does not flow unchecked, but rather distributes work in a controlled manner. The necessity of handling multiple draw calls efficiently is best demonstrated when looking at the individual graphical elements of a modern game scene. The streaming architecture of CURE allows to operate it much like common established APIs. We have implemented a planar water demo in CURE with waves and ripples animating the mesh. If we zoom in on one of the ripples, we can clearly see jagged edges that diminish the visuals. These artifacts are caused by the triangulation of quads that comprise the mesh. CURE allows us to solve this by defining a custom quad primitive that can change its triangulation dynamically based on a shader. We have reproduced an elaborate blending function inside CURE to preserve the original hues of blended isosurfaces. Notice how the rendering on the left receives a greenish tint, while the original colors can be easily distinguished with hue-preserving blending on the right. Of course, this also works in 2D with established artistic blending modes. A recent approach to foveated rendering involves skipping every other 2x2 area in the periphery of the image, since standard APIs handle pixels in quads for shading. Thus, only half of the pixels need to be drawn in these areas. The missing areas can then be filled in by a reconstruction stage. With CURE, of course, we are not restricted by quad shading and simply skip every other pixel in the image. This results in a higher fidelity output and even reduces the mean squared error of the final rendering.